All right. Hello, everybody. We're going to get started with today's talk right now. So, first off, welcome back to another Coffeeshop Astrophysics talk. It's actually been quite some time since we were last here at Anodyne, since our previous talk in March was at the very beginning of March. This one is at the very end of April. We've had quite a build-up to this talk because this is a very special and exciting talk that we're giving to you today. As I believe we mentioned back at the beginning of this year's talk series, we are celebrating Coffeeshop's 10th birthday or 10th anniversary since its founding. It was founded back in 2014. This is incredibly exciting. This is not the only event that we've had to celebrate. There was another event just last evening on UWM's campus to celebrate 10 years of Coffeeshop Astrophysics, but we're all excited that you could also come here today for this talk to celebrate with us. We've got the same usual opening slides. If you don't already follow us on social media, please do. You can either scan the QR codes there or just search Coffeeshop Astrophysics. We are luckily the only person or only group that has that name, so we don't have to fight for SEO rights or anything. If you have an idea for a future coffee shop talk, you can always approach us after one of the talks here at Anodyne, or you can reach us at that link there, which is just on our website on the contact page. Who are we? Well, Coffeeshop Astrophysics is, and always has been, groups of graduate students and postdocs at the University of Wisconsin-Milwaukee in the Center for Gravitation, Cosmology, and Astrophysics. There's all of our wonderful photos of our current members. We do want to make sure that we take a chance to advertise that if you're in Madison next month on May 21st, Astronomy on Tap Madison, who, if you may recall, if you were here back in March, they did give the March talk here at Anodyne, so we want to make sure we advertise any of their future events. If you happen to be in Madison on May 21st, check them out. They give some fantastic talks. Well, I am not actually the speaker today. I'm just here to give the introduction because to celebrate 10 years of Coffeeshop Astrophysics, we actually invited back some past and previous members of Coffeeshop to talk to you today, and I think that's going to be all for me. So what I'd like to do, it's my pleasure to introduce the founder of Coffeeshop Astrophysics from all the way back in 2014, Sydney Chamberlain.
Thanks so much, Gabe. Oh, that's very loud. Hi, everyone. It's really fabulous to see you all here, and it's pretty exciting to be back 10 years later and see that this is still going strong. So thank you so much for coming and being part of this and making this all possible. We thought today, there's three of us who wanted to speak a little bit, and we've all been engaged in Coffeeshop Astrophysics at different points in its evolution. And so what we thought we would do today is give you a little flavor of where folks from Coffeeshop Astrophysics end up going over time. And so we're going to tell you a little bit about our different career paths in STEM. And I just wanted to really flag for, anyone who's thinking about their career, the young folks in the room, you never know where your career is going to go. And hopefully this will help kind of ground that notion. So I work for a nonprofit, nonpartisan organization called the Nature Conservancy. I'm a project director there, working in California on climate change issues. And if you haven't heard of the Nature Conservancy, we're a global organization. We've got, hang on, I'm figuring out the slideshow. So we're a global organization. We have about 5,000 employees globally, over 900 which of our scientists, offices across the globe in 79 different countries and territories. And ultimately, we're working hard to tackle some of the world's biggest environmental issues. And you might think, what are some of those issues? Well, biodiversity loss and climate change are some of the biggest threats facing us right now. So we're working hard across the globe to really tackle those issues. And my role in all of that is part of the climate change program in California. So the way that the Nature Conservancy works in the US is that we have different business units generally in every state. So there's a Wisconsin chapter of the Nature Conservancy, for example, but I work for the California chapter of the Nature Conservancy, where I'm part of our climate team and really work to advance climate policy in California. So I'm kind of a climate change professional now. But I could also give a totally separate bio. And so this is also me. I went to Utah State University. I grew up mostly in Utah. Got my bachelor's degrees in physics and math in 2009, and then I scooted on east and came out here to Milwaukee to get my doctorate here at the University of Wisconsin-Milwaukee. And here, I was working on efforts to detect something called gravitational waves. So these are a signal predicted first by Albert Einstein a little bit more than 100 years ago, and I was working here at UWM with a whole bunch of other people trying to figure out, is there a way to detect these things? And ultimately, my work in this group really boiled down to data science and fundamentally to the question of how do you find a tiny signal that's buried in noisy data? This was like a huge problem in this sort of new field of gravitational wave astronomy. And I'm very lucky that I happened to be here in this particular fabulous city working with great people at the time I was, because just a little while later, we detected gravitational waves. It actually happened a couple months after I left Milwaukee. I went over to Penn State University, did a postdoc there for 3 years. And my first month at Penn State, we detected these gravitational wave signals that everyone had been looking for so long. And this was a tremendous victory in physics and science, and something that was really exciting to be part of. And I think some of my colleagues are going to say more about that today. But of course, maybe more importantly than gravitational waves, they had the opportunity to really start this coffee shop endeavor and just had this idea. I thought, you know, what's cooler than talking about stuff like black holes and neutron stars? And we know Milwaukee has an incredible coffee scene. I don't know if you all realize this, but I've lived all across the U.S. at this point, and this city has some of the finest coffee shops I've ever seen anywhere in the U.S. So, you know, neutron stars and black holes and coffee, I mean, what could go wrong, right? And so it's really fabulous, again, to be here 10 years later. So sometimes in the work that I do now, you know, I work a lot with folks in the Newsom administration, with different California state agencies, with other nonprofit organizations and academics, and people say, oh, how did you get started in climate change? And I say, oh, you know, I'm an astrophysicist, and I worked on looking at black holes colliding. And so usually when I try to explain that, I get this look from people, and they're like, what is she talking about? So it sounds like a really radical and weird pivot, and you might say, why and how would someone ever go and do that? But I think for me, it kind of boils down to the idea that when you spend a lot of time looking at distant objects and really seeing how vast the cosmos are, it really drives home the idea of how precious and unique and special this planet is, and how important it is to think about life on this planet. And actually, it also connects to something that, this is one of my favorite things. So Carl Sagan is this visionary scientist and science communicator. And he was part of the Voyager mission, which was launched in 1977 to study the outer solar system and interstellar space. In 1990, the Voyager spacecraft had finished its mission. It was just drifting out further and further. It was about 4 billion miles from Earth. And Carl Sagan had this idea. He said, what if we turn the Voyager spacecraft around and take a photo of the Earth from where it is now? And the photographer on his team, who happens to live in Sacramento, California, by the way, and I met him, he said, I don't think that's even possible. If you can get this photo, it'll be like a fraction of a pixel. But Carl Sagan said, no, let's just try it. And so they took this photo, and I don't know if you can see the dot. I had to make an arrow because the dot's so small, right? But that's Earth. That's a photo of Earth from 4 billion miles away. And in his book, Pale Blue Dot, Carl Sagan wrote this really beautiful excerpt and talks about how important this dot is. You look at this and you realize every person you ever know is on that dot. You know, every person who was ever born, existed, all the wars fought, all the science we've discovered, everything, just in this little tiny fraction of a pixel out. I think he says something like suspended in a sunbeam. And so it really does underscore the need to take care of this planet and to protect it and preserve it in ourselves, who we are part of that planet. So for me, that was a big part of wanting to make a career transition out of physics. So I ended up going and scooting back west. I went to Sacramento. And the way that I made this big career transition, I had always been interested in climate change. I was kind of worried about it. You know, you hear about it in the news and thought, oh gosh, that sounds really scary. And I knew I wanted to do work that sort of zoomed in. So instead of thinking about distant nature and sort of the cosmos, I was going to zoom in and think about nature on this planet. And so in California, there's a nonprofit organization called the California Council on Science and Technology. And this is an organization that was actually created by the California legislature a little bit more than 30 years ago with the idea that the state needed some entity that could help connect policymakers to science, because California values having science-informed policy. And so this nonprofit exists, and they provide a number of services. They provide expert briefings to legislators and agencies. They write commissioned reports. But one of the other things they do is that they run a science policy fellowship program. And every year, this fellowship program takes 15 or so different scientists from all different science fields, physics included, and puts them into a state service for a year. So you get trained and spend a year either working in the California legislature, one of the governor's offices, or for a California state agency. And so for me, I went to Sacramento. I was placed as a science fellow in the Senate Committee for Natural Resources and Water. So this is a committee that gets bills related to things like natural resource management, coastal resources, climate change, invasive species. And it was a big shift for me, because I was used to thinking about black holes smashing together, and suddenly the first bill I worked on involved an invasive species called the quagga mussel, and I remember thinking, what is a quagga mussel? But it was really dynamic and exciting work. There's so much happening in the legislature at any given time, and as a fellow, my job was to try to decide for a given piece of policy coming to our committee, is this sound policy or not? What does the science say? What are the unintended consequences of passing this bill? Is this bill going to work? Can it be implemented? Those are the kinds of questions that you're asking as a science fellow or as a committee consultant working in the legislature. And it was a fantastic way to cut my teeth on climate policy and really get up to speed with what California has been doing on climate change. And I know most folks here probably aren't from California, but California is a really exciting place to be working on climate policy. I would say California is kind of like a policy laboratory. It's a state that's invested a lot of resources in things like climate change and is really trying to push forward on environmental policy to make sure that we have a sustainable future. After my fellowship, I ended up going to the Nature Conservancy, so now we've kind of come full circle back. And I'm just going to give you a little flavor of what we're doing in the Nature Conservancy. I don't have too much time, so I can't get too far into the details, but happy to talk with anyone after. So I work on climate change, but it's not the only big environmental problem facing us right now. So this figure here is showing you, in the darker green color, a measure of biological diversity over time. And in the lighter green color, basically rising temperatures. It shows temperature anomalies. So you can basically see with the lighter green, that's showing you global temperature increase. And with the darker green, what you see is the trend going down. That's a biodiversity loss. And so we're seeing across the planet that globally, as temperatures rise, that's also tied fundamentally to a loss of the vibrant biodiversity across our planet. And those are big problems. We need biodiversity to survive. It's not just sad to lose biodiversity. It's actually something that we need for our own well-being and for the functioning of ecosystems. So this is a big problem, and it's something we're working really hard to address. And the way that my team is working to address that is through something called nature-based climate solutions, which you might not have heard of. I think most of the time when you hear people talk about tackling climate change, the conversation is, hey, we need to stop burning fossil fuels, which we do. We absolutely do. But when you think about the strategies that we have to tackle climate change, I don't think everyone immediately jumps to nature as a solution. But it's really interesting to think about it. So here's a quick reminder of the carbon cycle, which you might have seen way back in a class in school sometime. So the Earth is kind of like a closed system, and carbon is a really important element on our planet. It's something that helps make life possible. But our planet and the atmosphere around our planet really have a finite amount of carbon. And ultimately, carbon can move around in that system. So carbon atoms that are in the atmosphere can come back into the Earth, and carbon atoms in the Earth can go into the atmosphere. And ultimately, so we have this flow of carbon. On the Earth, carbon is stored in rocks, in sediment, in the ocean, and in organic living matter and living beings. And then it's released in the atmosphere through processes that include decomposition of organic matter or the burning of fossil fuels. And the primary way that humans interact with this carbon cycle is through the burning of fossil fuels or through land use. So actually, believe it or not, land use and climate change are really fundamentally tied together. If I go out in this picture here and I tear that tree out, then the carbon that's stored in that tree can be released into the atmosphere. Or if I go outside to a park and I take out all the vegetation and put a parking lot there, then the carbon that was stored there can be released to the atmosphere. So the way that we are planning our communities and developing our cities can have profound implications for climate change too. But on the flip side, the good news is that we have an opportunity with thinking about the way that we live with nature and planning our development to actually make a positive impact in the context of climate change. So the idea is that if we take a healthy ecosystem and we protect it or conserve it, we can prevent the carbon that's stored in that ecosystem from being emitted to the atmosphere and exacerbating climate change. Or on the flip side, if we think about ecosystems that maybe are at risk of being degraded or systems that have been degraded, we can go out and we can steward those systems well, or we can restore ecosystem functions to actually improve the ability of these ecosystems to hold on, to sequester and pull carbon out of the atmosphere and store it. So this is what we mean by the term nature-based climate solutions. It ultimately refers to stewarding, protecting, and restoring our lands in a way that help us to fight climate change. And the really cool thing about these solutions is that when you go out and you protect and restore and enhance ecosystems, you're not only fighting climate change, you're also providing a whole suite of other benefits that we all rely on and love, right? You're getting cleaner air, cleaner water, you're providing habitat for species, getting recreational space. I mean, who likes to go to the parks in Milwaukee's beautiful lakefront, right? We all love the recreational space. So these are solutions that fight climate change, but also provide tremendous other benefits. And not only benefits that are just nice to have, but help us to adapt to the unavoidable impacts of climate change that we might face now. So my work in California focuses on advancing this suite of tools. And what does that look like? Well, it looks like a couple of different things. California really has played a leading role, not only in the United States, but actually California is recognized as a global leader in tackling climate change. And the state has set ambitious goals to address climate change with the goal to achieve carbon neutrality by 2045. So California is working hard on all fronts to really tackle the climate change problem. But if I'm honest, for the most of the time California's been working on climate change, the focus has been on like decarbonizing buildings and electrifying the grid and other things that are also important, but nature has not always been an important part of that conversation. So a lot of my work and my team's work over the last decade has really been taking the science behind these solutions to the state and saying, hey, nature deserves to have a seat at this table too. And in fact, it's not just nice to have, we need to have it. If we don't have nature, then none of us can survive. So I do a lot of advocacy with the state, and that means showing up to various state hearings and providing remarks and providing feedback. But I also manage on-the-ground projects too. So in California, we have this really cool and weird region called the Delta. And it's basically a region in Northern California, kind of between the Sierra Nevada, so Tahoe, imagine Mount Tahoe, the Tahoe area, and then you've got San Francisco Bay, and ultimately an area where the melting snowpack from the Sierra Nevada would hit the Bay Area water. Historically, this area was a giant wetland, so just tons of wetland, lots of vegetation. It lies on a very critical bird migratory route called the Pacific Flyway, so it's a very important wintering destination for lots and lots of birds. But over time, over the last couple hundred years, human land use in this area, the Delta, has put profound changes on the landscape. Settlers came in, they drained the wetlands, and they did that because they needed to grow food, so they were trying to do agriculture. But unfortunately, when you take wetlands, these peat soils that we have in wetlands, they have a lot of really rich organic matter. And when you put that rich organic matter, you expose it to air, there's a chemical process that happens, an oxidation process, that actually makes the land sink or subside and release greenhouse gas emissions. And ultimately, this region in the state now is kind of on an unsustainable trajectory where we have all these little pieces of land people are trying to farm, but they've sunk below sea level. You're getting water from the bottom that's making it really hard to do agriculture. We've lost a lot of habitat for those important birds. So what we're doing with our project is to really try to reverse some of that. We're doing climate-friendly agriculture and putting wetlands back into place to reverse that ground subsidence effect, stop the greenhouse gas emissions, or at least reduce them, and to provide vital bird habitat. So I manage a 5,000-acre project there, and it's a lot of fun. I wish I had time to tell you more, but I want to make sure my colleagues have time to tell you about their exciting work. So I'm going to stop, but I'm really happy to talk to folks afterward. Thank you so much.
Hi everyone, my name is Lale. It's so good to be, I think I have to stand here, sorry. So it's so good to be here. Honestly, like 10 years ago when we started Coffeeshop Astrophysics, I never thought we'll be back here and also talking about completely different topics, which is very cool because I'm gonna shift gear here a little bit. Just a little bit of background. I got my PhD from Washington University in St. Louis. And at the time, I was working on the supermassive black hole that we believe exists in the center of our galaxy. What we know that is huge mass has been concentrated in a very small volume at the center of our galaxy. But on the other hand, also black holes are predicted by Einstein's theory through mathematics of his explanation of gravity with specific features. So my question during my PhD dissertation was how we can test those features that Einstein predicts for the central object that we believe is a black hole. That was part of my research. The other part of my research was about dark matter. It's a mysterious substance of our universe, almost making up to 25% of our universe. The normal matter, all the galaxies and the stars and everything we know, is just 4 or 5% of our universe. The rest is the 25% dark matter, and the rest that's even more unknown to us is dark energy. But we know that there is a halo of dark matter around our galaxy, and what I worked on was how these supermassive black hole will impact the distribution of dark matter. That was another part of my research that I worked on while I was at Washington University. After my PhD, I came to UWM and worked on gravitational waves as a member of LIGO collaboration. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And the quest was to find the signal, the ripples in the fabric of a space-time that will be created when two black holes, or one black hole and one neutron star collide. I was like so lucky to be at LIGO collaboration during the detection of first ever gravitational wave signal. LIGO had been going on for more than 25 years at the time, and I was part of it when the signal hit the Earth after like traveling for so long in the space. I was working on finding intermediate mass black hole through LIGO data because that's another mystery that at the time we knew that we have normal black holes, like 4 or 5 times of mass of the sun, and then we have like million times mass of the sun, like supermassive black hole. But in the middle, these intermediate mass black holes were kind of gap. We never had observed anything suggesting that these intermediate mass black holes exist. LIGO is kind of closing the gap with more and more observations, but actually I'm not that close to that research anymore, so I don't know exactly what's going on, but it would be super cool if they find it like 200 times mass of a black hole in their signal. So the detection happened, we celebrated it, it was amazing, and I had these big pivot in life that I didn't want to stay in academia anymore, and I wanted to go and work on like more everyday, kind of like everyday life problem type of stuff. So what I did was I switched to data science, and I moved from Wisconsin to California. I was in Silicon Valley, starting to work as a data scientist at Facebook. That was like the best way that I could like make the pivot. And as a data scientist, I actually got an interview because people were asking why I did that pivot. Like LIGO had won the Nobel Physics Prize in 2017, and 2016, right before that, I moved to Silicon Valley and started as a data scientist. It was a fun interview, and to summarize why I did the pivot was like, yeah, working on more everyday life problem. And to be honest, I was just curious. I was like, okay, I saw and I had the best kind of case scenario that could happen in academia. Now let's see what's going on in the tech world, and that was the main reason. As a data scientist, I worked on newsfeed ranking a lot, like how we can like rank newsfeed. At the time, Facebook was hot still, not anymore. But we were like working on like, okay, how we can like rank the contents better. Specifically in India, I was focused because it was the biggest market in terms of monthly active users for Facebook at the time. It probably still is. And but people in India use Facebook way different than people in US. Actually, they maybe use it more like a LinkedIn, so the content needs to be ranked like accordingly. So I was like studying that. Another pivot was going to happen for me, and I thought, okay, data science in physics is much cooler and cleaner, but like in the tech is different. Like it was a big culture shock actually going from LIGO to Facebook at the time for me. And funny fact, talking about efficiency in the business world, my name is Lale, and everyone called me L, and that's how I'm like going now. Like my name is L, no one calls me Lale anymore. But yeah, we had like lots of like good research at Facebook, but at the same time, I was like, this is not why we did the pivot. So another pivot coming from data science to product manager. Just a little bit about this role. People think product manager and project managers are the same thing, but they are really not. Product managers are, you can think of it maybe as a mini CEO of a small part of the company. So you have a mission, you have a problem to solve, and you have a team. So I have a team of like engineers, data scientists, UX designers, and data scientists. We all work together to solve a problem and see like how successful the solution is. So I did the pivot to product management. It was like a jungle gym, you know. I had to like get like down ranked and get a salary cut and everything. But I really wanted to try product management again. And as a product manager at Facebook and Instagram, I worked on launching like a private encrypted messaging, like the way that WhatsApp is everything is encrypted, so no one knows the contents of your messages. We did that for Instagram and Facebook, which was like a more than 2 years project that took like so many people to make it happen. I also worked, because I had a data science background, I got this project of working for music partners of Meta, I mean Facebook at the time, because these big companies wanted to know how much their music has been used on Instagram and Facebook when people like add a story and like put a song on it and all that, because that helps them to pay their artists, like the royalty that they have. So I built this like tools that was about, okay, how much their music is being used across like Facebook and Instagram. And because of that, I actually got very interested in like music streaming services and like how music streaming, personalization, machine learning, how we like rank content for people, what type of music and all that. So after being at Facebook and Instagram, I actually moved to Amazon Music. It's an app that Amazon has, and we compete with Spotify and Apple Music in US especially. And my job is to create community for these music streaming services, which hasn't been a problem that's been solved at scale. Like Spotify or Apple Music hasn't got the solution for how we can connect people to discover music through each other, and also connect around the music, like strangers who might have a similar taste across the globe. How we're gonna find ways for people to appreciate music in a deeper level, like find more people, find more music they love and all that. I'm at the very beginning of this journey. I'm just like in the privacy and profile world right now, like trying to figure out how we can unlock this. But that's my kind of everyday life now until like hopefully the next pivot. Happy to talk about like transitioning from science to tech, and also inside the tech from data science to product management. But I feel like it was an amazing journey, and Coffeeshop Astrophysics was a big part of it. So thank you so much for all the support throughout the years, and happy to answer any question after Casey's talk.
All right, thank you. Yeah, so in terms of career paths, I put mine up here as well to see if anyone finds it useful, I hope, but I'm going to be talking about where I'm landed these days after having been a part of this coffee shop group, so it's really great to be back. But after, I started off similar, I think, to Sydney in doing a Bachelor's of Science in both physics and mathematics at the University of Redlands, Southern California. And after that, I moved out here to Milwaukee to participate in the PhD program. After 7 years of that, I completed my PhD having studied gravitational wave astrophysics in pulsar timing and topics such as that. And I was able to then secure a postdoc, and I now work at NASA Goddard Space Flight Center. So formally, my employer is the University of Maryland, Baltimore County. There are sort of two types of people that work at NASA in general. You've got the civil servants who are directly employed by the government and work directly for NASA. And then you've got contractors who are actually the majority of the workforce when it comes to NASA. And so we are contracted through other agencies and other locations. In my case, it's UMBC. So for the purpose of this talk, I figured it'd be mostly interesting to maybe just kind of go over NASA in general and talk a little bit about that, and then I'll mention sort of the research topics at the very end that I actually participate on, and you're welcome to ask any more questions about that. But in general, NASA as an entity spans across the United States and comprises numerous centers and facilities, which you can see all listed here in this image. And some of these locations are well known for certain areas of expertise. So for example, when you think of perhaps the rovers, Curiosity, Spirit, Perseverance, all of the Mars rovers, or the missions to the various planets in the outer solar system and the inner solar system, those are often led and pioneered through JPL. Then you've got, for example, the astronaut corps lives and trains in Johnson Space Flight Center. A lot of the rockets are launched out of Kennedy. And if we look at where I am, I'm here just outside of Washington, D.C. at Goddard Space Flight Center in Greenbelt, Maryland. And Goddard is known for, one, it's actually the largest of the centers at NASA in terms of the number of people that it employs, which is about over 10,000. So we've got that 10,000 comprises the scientists, engineers, management, all the people that work in the various buildings. So it's pretty much everyone, but it's a very large number of people. It's a very large campus. And we are also well known for developing and assembling many of the telescopes that get launched into space. So this is an example back, you might remember, when Webb was still being built. That was being assembled in various locations throughout the US, but then it all came together at Goddard and was assembled at Goddard and then launched in 2020. So that was Webb. We've got, for example, also the Hubble Mission Operations Control Center is located at Goddard. So Hubble is still being controlled through Goddard. And the next flagship is currently being assembled at Goddard, which I will talk a little bit more about, which is the Roman telescope, which is quite exciting. In terms of the work that NASA does, NASA is, again, the National Aeronautics and Space Administration. So aeronautics and space are the two key words there. And these are the 6 subdivisions that comprise everything that NASA is interested that you can see. So given that my background, having done a PhD here in Milwaukee in physics and astrophysics, I naturally fall into supporting the Science Mission Directorate. So I'm only going to focus on that one for the rest of this talk. And if we dive into the Science Mission Directorate and we peel back the onion layers even further, then there are 5 key areas that NASA is most interested in terms of science that they do. So those being heliophysics, which are the study of our sun. We've got earth science, which is the study of our planet. Biological and physical sciences, so human presence in space and biology in space in general. Then you've got planetary science division, which is basically all the planets in our solar system apart from Earth. And then finally, the astrophysics division, which is everything outside of the solar system. So again, my background being gravitational wave astrophysics, I fall into the astrophysics subdivision in the Science Mission Directorate. So that is where I currently work, and the types of projects that I work on support this part of NASA. Now, I realize you probably can't all read it from a distance because all the text is quite small, but what this image is showing, I absolutely love looking at this. This is the science fleet that NASA commands. And sometimes we kind of, perhaps it's easy to forget that, like, well, we think of Hubble, we think of Webb, but these are all of the telescopes in just the Science Mission Directorate across all 5 of those subdivisions that I mentioned, from planetary, helio, Earth, bio, and astrophysics. These are all the names of the current and the near-term telescopes which are currently being developed at NASA. So some of these haven't launched yet, but they are on the docket and being developed currently. So if you were able to scrutinize this list a little bit more closely, you might notice some more familiar names like the ones I mentioned. Webb and Hubble are both on this list. You'd also be able to find the Curiosity and Perseverance rovers, the upcoming Titan mission, Dragonfly is on this list. So there's some really cool missions out there, and this is why I love working at NASA, because I just think this is so cool. That this represents like all the work that we do just in the astrophysics division, or sorry, just in the Science Mission Directorate. Now, in terms of near future, or near-ish future, if we focus mostly on the efforts that Goddard is interested in at the moment, this is sort of a roadmap to look at, and I'll point your eye to a couple things. So the Hubble mission is what we would refer to as a flagship class mission, arguably the most famous telescope built in history. Webb was also is also a flagship class mission and is just pumping out the science on a day-to-day basis now. It's really exciting to see Webb. The next flagship class mission is currently being assembled at Goddard Space Flight Center that I mentioned is the Roman Space Telescope. So you'll be hearing about this more and more in the news in the coming years, but it's slated to launch, I believe, around 2027, which actually surprises me because flagship class missions don't come around super frequently, and we're already getting one within the decade from having just got Webb. So this is going to be exciting. A little bit further out into the future is the mission that is most near and dear to my heart, which I'll talk a little bit more about, that I'm helping to support. LISA is the name of this particular mission. It'll be the first gravitational wave observatory launched into space, and that is what I was hired to work on at Goddard. So that is currently targeted for about 2035 at the moment, so that's going to be a little bit further out. And then even further out, but also still interesting to keep in mind, a lot of effort is currently going into designing the Habitable Worlds Observatory, which will be the next great flagship mission beyond Webb and Roman, which is sometime in the 2040s, so quite far out still. All right, so I, as I mentioned, was hired to work as a postdoc at Goddard on the Laser Interferometer Space Antenna. So this is the LISA mission. It is actually being led by the European Space Agency, so they're taking the lead, but NASA is supporting it. And in terms of the design of it, it's a 3-satellite constellation, we call this. So it's each satellite itself, perhaps nothing spectacular, roughly the size of a small vehicle. But what is impressive about this is they're going to formation fly in the shape of a triangle. And while they're not physically tethered or connected to each other in any way, they'll be shining a laser beam between each spacecraft. So these are essentially the arms of the spacecraft, similar to LIGO, which is in the shape of an L, and it shines the laser down both arms. But the arms on this thing will be 2.5 million kilometers long. To put that in perspective, because that's just a big number to me, but someone put it into perspective recently, which I really appreciated, is the triangle itself, if you were to take that thing, you could put the entire sun in the center of the triangle. It wouldn't touch the edges. So this is going to be absolutely enormous. So big, in fact, it won't be orbiting Earth. It'll be in Earth's orbit, orbiting around the sun. So it'll be in an Earth, what we call an Earth trailing orbit. This is very special. I'm not even 100% sure if we've done this before. I'll have to look into that. But that'll be exciting. And the target launch, like I said, around 2035. So why are we doing it, and what's the purpose that it's going to serve? Well, I make the analogy or the comparison with the world of traditional telescopes and electromagnetism and light. So when we talk about light, and Coffeeshop I know has done lots of talks on this in the past, we point out that there's a whole spectrum of light, and we have to build different types of telescopes to see different parts of that spectrum, because one telescope just can't be made to do all of it. So for example, we have the Hubble telescope, looks mostly in the optical light, visible light. Webb looks in infrared. We've got Green Bank and Chandra looking in radio and X-rays. So we build different telescopes to cover the entire region of the electromagnetic spectrum. And in a similar fashion, gravitational waves, they also have this huge range, what we call spectrum as well. And so we need different types of observatories to see all the parts of the gravitational wave spectrum. The terrestrial detectors here on Earth that we've built, they were the first successful detectors. So, for example, the LIGO observatories, Virgo, Kagra, these are all the terrestrial-based ones. They see at one extreme end of that gravitational wave spectrum. Recently, and I know Coffeeshop just did a talk not too long ago on this, Pulsar Timing has started to detect the presence of gravitational waves in their own data set, and that is actually on the opposite end of that gravitational wave spectrum from LIGO. And LISA will fill the gap right in between, so in sort of this middle regime. So that's why it's important, because we have nothing that can actually detect sources in that regime at the moment, and LISA will fill that gap. So we'll be learning a lot of new science from this particular observatory. Now, again, I could go into a lot of time on each of my projects sort of things, so I'm just going to briefly mention what they are, and you're welcome to chat with me afterwards if you're curious to learn more. But the types of projects that I work on supporting LISA at NASA include, for example, data analysis. So I'm helping with the software development at NASA. One of the big challenges will be when LISA sends all the data back to Earth, we then have to post-process that and suss out all of those gravitational wave signals from the data itself. Every once in a while, you'll get a spurious, what we refer to as a glitch, which is just an artifact. It's not anything astrophysical. It's oftentimes something happening in the detector itself. LIGO has this happen all the time to them, and it was a similar problem that they also had to solve. So one of the problems we have to be able to do is identify glitches from actual real astrophysical signals and subtract those out of the data set so that they don't corrupt our data. Another project that I've just recently started working on, which is fairly nascent in its conception, but it's of interest to some people, and we're kind of starting to try to understand if it'll be a thing or not, but we might be able to detect exoplanets with LISA, which would be a very intriguing possibility given that it was never designed to do that. But the idea being that the most common source that LISA will detect will be binary white dwarf stars generating gravitational waves. We will be detecting thousands of these within the Milky Way galaxy the moment we turn on LISA. And the idea was if one of those white dwarf stars happens to have an exoplanet orbiting around it, which would be a very exotic system, I believe, then it might actually change the signal in such a way that we could identify that it has some kind of companion orbiting around it, which would be really cool and a brand new method for detecting exoplanets. And finally, being at NASA, I'm also very interested in mission development and concept design, so I've also been sort of helping with some of those efforts. It's a great place to get involved because you basically get to have direct input on what the future great observatories are going to be like and what potential future missions might look like, so I've also been kind of working in that area. So those are sort of my areas of interest. But I think that kind of wraps it up, and so I'll hand it back to Gabe, I guess, so you can give this last slide.
Yes, so before we go to the Q&A session, can we please give one more round of applause for all three of our visiting speakers today? We're so thankful we're able to come out to Milwaukee. This is our standard last slide. I have to make sure that you all know we have one more talk for our spring semester talk series that is going to be in 2 weeks on May 11th. The topic, keeping in the theme of our 10-year anniversary celebration, we're going to be covering the last 10 years of astrophysics, because astrophysics has changed quite a lot since Coffeeshop started back in 2014, and we're going to cover all of the cool things that have happened over the 10 years that this group has been alive. Again, you can find out information on our website. Make sure you're following us on Facebook and on Instagram to get up to date about our events. And also, of course, we upload all of our talks to YouTube, including this one. So make sure you check that out and share it with your friends and family who may not be able to make it to these talks in person but could be interested. And then lastly, since this is our 10-year anniversary celebration, I really do want to thank each and every one of you who have come to these talks, not just today, but the talks over the last 10 years, because we can't give these talks if we don't have anybody to give them to. Out of curiosity, I don't expect anybody to raise their hand, but was anybody here, like here today, who was also here for the first talk back in 2014, or any of the... We'll take it. I mean, thank you so much for everybody who's been coming to these talks, not just today, but for 5 years and 10 years. So thank you to all of the Coffeeshop superfans out there, and hopefully the budding superfans as well. And we look forward to celebrating our 20-year anniversary about this time, maybe in 2034. With that, I'd like to invite our three speakers up here again for a Q&A session if any of you would like to ask questions.